Okay, so so far we have seen the perfect testing, construction of proof testing, the perfect testing. There are many good techniques of application of hash, which is used in many crucial cases. For example, we have a file of password, and you can notice that in some website, if you type wrong password, it instantly says it is the wrong password. But if you say type right password, it takes some time and then login and web page appears. Okay. So reason behind that is some website maintain Bloom filter for the for their password. Okay, and instead of going and checking into the physical database, they first check it in the Bloom filter. If Bloom filter says no, this is not present, then it is not present, and instantly reply the thing. Bloom filter is used in many other places for like table join in database, in network broadcasting, whether some node is available or not. Okay, there are many more beautiful applications. It is totally based on very simple hashing technique. Okay, so let's see how this is done. It was developed by Barton Bloom. That's why it's named Bloom filter. Okay. So Bloom filter is basically it is designed to check the set membership. Means given a collection set of elements E1, E2, let's say En, and given a query element EQ, we have to say whether EQ belongs to S or not. Bloom filter check that thing without verifying physically in the how. So first of all, there is a B tag. B tag is basically, let's say the size of the B tag is M. Okay. B tag means every index is a bit either 0 or 1. Initially all set to 0. Okay. There is a bit array and all set to 0. So since these are bit, even if M is very large, the uh, memory requirement for this array is very less because these are all bits. Okay. Now what we do? We take k number of hash functions. Okay. Let's say we have h1, h2, okay, to hk. For the time being, let's assume k equal to 3 and we have 3 hash functions. Okay. So what we will do, like normal hashing, this h1 will evaluate the element key of the element u1, u2 and insert of the element. Insertion means it will give some index in this table, and what it will do, for example, let's say h1 k1 is basically the second position. It is going to the second position. So what we will do, we will overwrite it with 1. Whatever the value, previous value, it may be 0, it may be 1. If some element mapped to some position, we will set that value to 1. Okay, irrespective of the previous. If it is 1 already, it's okay. Still you overwrite. Okay. Whatever the position it will suggest, we will overwrite. So what we are going to do, we are going to insert all the elements using the first hash function h1. Okay. Then we will insert all the elements using second hash function. Then we will insert all the elements with kth hash. So at the end, the bit array will look like there are some zeros, till some zeros, and lot of ones. Okay, this long bit array will have many entries 1 and some entries 0. Then maybe some overlapping. Means some position is set 1 by some particular element using some function, other element using some function. Okay, that is. So at the end we have a bit array of some 0 and some. So how we will check this set membership? Now let's say we have this query element EQ. Okay. What we will do? We have three hash functions. So we will evaluate the key of key q using h1, using h2, and using h3. Okay. We'll get three different positions. This, maybe this, maybe this. This position may not be sequential. I have wrong sequential. But maybe arbitrary location in this detail. So now, suppose some of the entries are 0. Is EQ present in the set? If EQ is present in the set, then EQ must be inserted into the bit array. And if EQ is inserted in the bit array, then all this hash value must be set to 1. Okay. So if it is some value is not set to 1, it means EQ is not present. So we don't need to verify physically in the set or in the long hash table whether the value is present. Okay, we can directly say that it is not present. Okay, by checking a very small bit array. Okay, but if it is present, that all the bit may be 1, but there is a issue. What is the issue? Maybe some element EQ is not present, but due to the insertion of other element by some hash, all this position may be already occupied with 1, set to 1. That may happen. That scenario is called false positive. If the element is not present, we can, with probability 1, we can say the element is not present. There is nothing wrong. Okay. But if the element is not, if some position is 0, then we can, with certainty, we can say that the element is not present. But if all the positions are 1, it does not guarantee that the element is present. Element may be present, but all the position may become 1 due to the insertion of some other value. Okay, that scenario may happen. So that is called false positive. Okay. Now we can compute the probability of false positive, and we can make this probability greater or lesser by choosing the size of the array, and there are two parameters, number of hash function k, and there is one more parameter m, size of the array. So if we change these two parameters, we can reduce the probability of false positive to almost 0. Okay, 99.99% probability of certainty that there is no false positive. So that will be 0.00001 false positive may be set to that. Okay, that is possible. How? That's a very simple mathematics. We can check. Let's say we have one element, one has function, and this table. Okay, what is the probability that one element is inserted into the table? So what is the probability of one? Okay, of some position is 1 by n. Okay, some element is inserted in some position. So probability of 1 is 1 by 1 using 1 as function or 1 element. Okay. So what is the probability of 0 when we have 1 as function, 1 element is 1 minus 1 by n. What is the probability of 0 when we have k as function? What is the probability of 0 when we have k as function? It will be 1 minus 1 by m to the power k. What is the probability of 0 when we have k as function and we have inserted n element? This we have computed for one element. If we have n element, then it will be k into n. Okay. Now this is the probability of 0. Okay. When we have used k as function and n element. What is the probability of 1 after using k as function and n element? That is actually required. Okay. So that will be 1 minus 1 minus 1 by m to the power 10. Okay. Now look at this false positive scenario. False positive scenario means all the k positions are occupied with 1. We have to calculate the probability of that scenario. All the k arbitrary positions are set to 1. What is the probability that k position set to 1? This is what we have computed for one position. If we have k position set to 1, then we have, and this is the probability of false. Okay. So now we can change this parameter value. We can increase the, if we increase the size of m, this 1 minus m will become infinite symbol. Very more we increase the size of m, 1 minus m will become very small and it will be almost. Okay. So the probability of false positive will become 1 minus 1. So it will become 0, almost 0. So increasing the size m will reduce the probability. Okay. Again, this k. Okay. K, if we increase k, then also the probability will reduce. Why? Because this is a fraction. If we increase the power of the fraction, it will be a smaller fraction. Okay. And the probability will reduce. So we can tune k and m to get a very nice probability value of the function. Now, in practical scenario, how this blue filter is. For example, take the case of join a person in data. Heavy join. Let's say we have two big table and we have to, there are some entries, there are key values, the element rows, and we have to, these are gigantic tables, maybe 10 GB, 20 GB long, and we have to join this table in data. Okay. So what, and this table may be in the different system, so we have to transfer the table through the network, then we have to join physically. So that operation is costly. When we join the table, we see that not all the element keys are matched. Okay. Whatever the subset is matching, only we join those elements. We join. Okay. So instead of shifting the table from the beginning, what we can do, we can create a Bloom filter for the table, pass the Bloom filter to the network. Why? Because Bloom filter will be reiterate, so it will be small size. So passing it through the network will be very cheaper. Okay. We can check what are the elements present in the table 2 and table. So we can check early, and we can transfer the part of the table through the network to reduce the network operation. That will make the join process faster. It is called Bloom join. Okay. For network, wireless network or wired network, generally every time ping for the element which are the nodes alive in the distributed system. Okay, so and that is basically communication goes through over the network. So we can maintain some small Bloom filter of the alive nodes, and that we can keep in the network buffer, so that the machine can check in the from the network that whether what are the elements present or what are the elements not present. Okay. So there are many beautiful applications. We in some lecture will come with some project using Bloom filter. Okay. So that's all in this Bloom filter.